You have 15 minutes. Thank you.
Monday, you could be muted. Check. We can't hear you.
Mwende, we can't hear you. Mwende. We can't hear you, Mwende.
So Monday, it looks like you have issues with the audio. I suggest that you remove the earphone and use the computer audio. Try that.
Hello, can you hear me now?
Yes, yes.
Okay, then. Well, I was saying that the outline of my presentation is I take you through introduction, materials and methods, results and discussion, and then a conclusion. Well, in this study, we investigated the effects of structure formation methods on the optical and electrical properties of monometallic colored perovskite thin films. And this study was significant because of its wide applications in photovoltaic industry, mostly in solar cells as absorber material, in lasers, light emitting diodes, and photodetectors. And the reason why we chose to use organometallic colored perovskite material is because of its easy processability. The cost of making the material was low. It has a high UV-VIS absorption. It possesses a direct band gap, and it has a flexible electronic configuration, so we can easily tune the optical and the electrical properties during the preparation methods. In our study, we used 3 materials. We used lentil iodide powder, methyl ammonium iodide powder, and the methyl formamide solvent. All these materials were used without any further purification. We used 2 methods to prepare our fumes: single-step solution deposition method and 2-step solution deposition method. In single-step solution deposition method, we started by preparing methyl ammonium lead iodide precursor solution by dissolving lentil iodide powder in methyl ammonium iodide. And then we deposited our fumes using spin coating method. And later on, we annealed the fumes using different annealing temperatures ranging from room temperatures to 170 degrees Celsius. And after that, we measured the thickness of the fumes to ensure that all the fumes that we were characterizing and uniform thickness. We measured the values for absorbance of these fumes using a UV-VIS spectrophotometer, and we also measured the heat resistances of these fumes using 4-point probe equipment. We also used two-step solution deposition method to deposit our fumes. And here we prepared the precursor solutions of lentoiodide and methyl ammonium iodide separately by mixing the polders in DMF solution. And after that, we did two-step deposition. We started by depositing lentoiodide using a spin coating machine. And after that, we dipped the fume of lentoiodide into the solution of methyl ammonium iodide on different dipping times, ranging from 1 hour to 96 hours of dipping. And after that, we measured the thickness of the fumes and characterized them using a spectrophotometer and a 4-point probe equipment. So these are the results that we obtained from the measurement of the absorbance using the spectrophotometer. We used Stark model to estimate the values for the optical band gap energies. And graph A is showing the values for it's showing the results that were obtained in single-step solution deposition method, the value of optical band gap energies in relation to annealing temperatures. And we see that as the annealing temperatures were increased from room temperature to 107 degrees Celsius, the optical band gap energies decreased from a value of 2.23 electron volts to a value of 2.09 electron volts. So this decrease in the optical band gap energy might have resulted due to the increase in the crystalline nature of these fumes as a result of the reduction in the number of grain boundaries at the annealing temperatures were increased. So these results are similar to the results which were obtained by Atta and co-workers in the year 2018. And the second graph B is showing the values for the optical band gap energies for the fumes that were prepared in two-step solution deposition method through varying of the dip coating time. They are showing a decrease in the values for the optical band gap energies as the dip coating times were increased from 1 hour to 96. We see that as this dip coating time were increased, the values for the optical band gap energies decreased from 1.57 to 1.52 electron volts. So this decrease in the values for the optical band gap energies can be explained as a result of increased molecular wandering, which results from an increase in the molar division of the molecules as the dip coating times were increased from 1 hour to around a value of 48 hours. And we see that we obtained the optimum value for the band gap energy at the 48 hour, and beyond this hour, the values remained constant. So these values we obtained in the second graph where we were varying the dipping times. They are lower than the values that were obtained by Wang and co-workers in the year 2017. They obtained a bigger value of 1.959 electron volts. And a decrease in optical band gap energies indicates that the energy that is required to facilitate the movement of electrons from the valence band to the conduction band is reduced, and this means that we have more electrons moving faster to the conduction band where conduction takes place. And these are the results which are showing what was happening to the resistivities as the annealing temperatures were varied in single-step solution deposition method, and as the dip coating times were varied in two-step solution deposition method. And we see that in the first graph, where we did the experiment that was performed in single-step solution deposition method, there was a decrease in the resistivities of the fumes as the annealing temperatures were increased from 30 degrees to 170 degrees. And we have said that this decrease in the fume resistivity shows that there was an increase in the electrical conductivities as it's demonstrated in this equation. We see that the conductivity of fumes is indirectly proportional to the fume resistivity. So as the values of the resistivity is decreasing, we see that the conductivity is increasing. And for the fumes that were prepared in two-step solution deposition method, we see that
yes, Manda, equal.
Resistivity decreased as the values for the deep coating times were increased from 1 hour to 96. And these values decrease in the resistivity shows that there was an increase in the electrical properties of these fumes. In conclusion, as we were varying the annealing temperatures and the deep coating times, there was the narrowing of the optical band gap energies of the fumes, and there was a decrease in the fume resistivities. Both these results indicate an increase in the electrical conductivity, which enhances the performance of these materials. And as we compare the values obtained in single-step solution deposition method and two-step solution deposition method, two-step solution deposition method yielded better results, which are optical and electrical properties as opposed to single-step solution deposition method. And I thank you all for listening.
Thank you very much, Mwende, for nice presentation. Members, just keep your questions till the end of the session. Now we invite our second speaker. We invite our second presenter, who is Ahmed Al-Kabir. Mr. Ahmed, please share your screen with us. Thank you. Ahmed Ali, will you please share your screen? Ahmed, can you hear me? Hello?
Chair, I don't seem to see Ahmed.
He was around.
Yes, he was, but now I'm not sure whether I can see him.
Yeah, I don't see him either also. So I think we can go to the next speaker and then we can come back later.
Okay, let's go to the next speaker, Mr. Charles Mogunde. Please share your screen. Thank you.
Ahmed is in again.
So Ahmed is around.
No, just go ahead, Charles.
Dr. Victor, you can share kindly.
Ahmed, will you please share your screen with us? Oh, that's Joachim. Okay, proceed, Joachim.
Okay. Is it full screen, mine?
Are you hearing me? Are you hearing me?
Yes, I'm hearing. So I proceed to present. Yeah, slide 1. I welcome Msseesa members to this presentation, whose main objective was to enhance light absorption of pensetum, parium, and the synodom dactylon natural pigment photosynthesizers for DSSCs. I'm Ogunda Charles, a PhD student at the University of Nairobi. My supervisors are Dr. Waita and Professor Msembi Robinson. So slide 2, kindly. Kindly, next slide, slide 2. A dye-sensitized solar cell comprises of many components. One of them is a photoanode, an electrolyte, counter electrodes, and the dye. The main focus of this study was on the dye, which must have a wide absorption spectrum, which can absorb through UV, VIS, NIR, and also it must be cheap, that is cost effective, so it does not require synthesis processing, and also it must be environmental friendly, meaning it's not toxic. Also, it should have an anchoring groups to adsorb to a metal oxide. These were the qualities of a dye which were described by previous researchers, which have indicated below, Miatkain 2018 and others. Slide 3, please. Next slide. Yes. Now that we focus on the dye has also some components which are the chlorophyll, anthocyanins, carotenoids, flavonoids. These components, some are soluble in organic solvents like chlorophyll, and the water can dissolve anthocyanins. So to extend the absorption spectrum, all of these components must be present so that the absorption, am I audible? Hello?
The sharing has stopped. We don't know why. The screen.
Yes, Dr. Odari was assisting me to share. Yes, I stopped at slide 3, so I moved to slide 4. Yeah, the anchoring groups, functional groups are visible. You see chlorophyll as carboxylic groups, phosphoric, and these are the anchoring groups, functional groups that attach themselves to a metal oxide, which conducts electrons from the photosynthesizers. So carotenes are there. Also, we have anthocyanins and we have chlorophyll. Next slide. Now, the materials that were used to extract the dye from are shown there. On the first penstem purium is Napier grass and also Cyanodon. Dactylon is also Bermuda grass. These grasses were chosen because they seem to be resistant to drought, and also they can persevere any stress. This was shown by researchers shown below, and they take long to dry, and also they can resist winter and other climate conditions. Like the Bermuda grass normally is used in play fields where sports people play around but still remain green. So this research attempts to see whether this resiliency can be transferred from these plants to solar cells, which can be stable. Next slide, 6. Now these grasses were plucked. After plucking, they were cleaned. I'm in slide 6. They were cleaned with the ionized water to remove any impurity. They were dried slowly. Next slide 6, kindly. They were dried in a shed for about 10 days. They were crushed. After crushing,
I think the person moving the slides has gone to sleep.
yeah, you can see from the slides, we have the border of the green plants. We have also the carbon. The carbon was obtained from the ordinary charcoal, which was crushed and ground into fine powders. We move to the next slide, please. Next slide. Now the green solid and the black solids were mixed in those ratios of masses. We see ratio 1 to 0, 4 to 1, 3 to 2, 2 to 3. Next slide, where there is a table. After mixing these ratios, you can see the label S and the label T. These labels are essential to this research because the ratios are quite significant on the part of the dye. Now, these two are the ratios to watch. The next slide, slide 8. After mixing was done, they were all put into acetone of 100 ml, and also 5 ml of water was added, and they were put in a DUV spectrophotometer for analysis between 200 and 1000 nanometers. The advantages of this, the procedure is non-toxic, even the reagents used. There is simplicity in preparation and the ease of replacement. You can replace easily these materials, these types of grasses. Next slide, 9. Beer-Lambert law explains the relationship between absorbency, molar absorbity, concentration, and also the path length. MEAT 2018 gives a formula which can tell us about the conversion efficiency, light harvesting efficiency of these absorbers that we obtain. Next slide, 10. The tau correlation was used to obtain the curve that was giving us the energy band gap, and absorbency, which was obtained, was utilized. Slide 11. We realized that the highest absorbency, which is just below 100, was purely carbon, and also the least was purely the dye. But in between the ratios, you'll find all the trends, there's a decreasing trend, but you realize that the absorbency is about above 60%, and the ratio of interest is 2 to 3 S. If you look at the S, you realize that the absorbency is just above 65. This was selected because of higher dye content. And if you selected carbon, the highest absorbency, it means you'll not have any kind of electrons produced. And absorbency here, you realize that previous research, which is quite similar to this one, which was done 2019, the absorbency was stable up to about 500 nanometers. But this one is above 900 nanometers. Next slide, 12. Absorbency is compared to light harvesting efficiency, which can be shown there with the graph. You will see that the efficiency is much higher, above 80%. And similar research that was done you realize that 400 nanometers, that is the limit point of these plants that were used, thick dye and henna dye. This research which was done in 2018. And this dye now, I can call it from the names that, the ordinary names like we have Bermuda grass, Napier grass, and also carbon. So C for carbon, BE for Bermuda grass, NA for Napier grass. So if this one is very successful, this the name, I'll give it to this dye. Next slide, 13. The band gap was determined by tire correlation, and it lies just 1.86 electron volts, and it is within other research which was done by Ramadan and Ahmad in 2018 and 2019. Next slide, 14. Now I conclude that this research actually, which focuses on enhancement of absorption, which was successful up to a point of 70%, and also the spectrum of absorption, it highly exceeded the previous research, which reaches about 500. This one is about 970 nanometers of wavelength. And also this dye is abundant, and it is expected to exceed the percentage conversion efficiency of ruthenium dyes which are currently being used, which give a yield of 10 to 11%. And this one, I say that the energy band gap provided tells us that there is the transition of electrons from one state to another, that is HOMO to LUMO. The energy required is very minimal. Next slide. Slide 15. Kindly, slide 15 is a summary of what I've already said. This work is an ongoing work. It's not yet over. There are other experiments that are required to confirm the stability of this dye. So I thank you all for your time. Thank you.
Thank you, Charles Mugundo, for nice presentation. We now go to another presenter. Ahmed Al-Kabir, can you please share your screen with us? Thank you.
Hello, hello. Can I start now?
Yes, Ahmed, you can start.
We can't hear you.
I'm sorry for this coming late. Thank you, Chair. Thank you, everyone. Good afternoon. My abstract is apart from my PhD proposal, supervised by Professor Nyongesa and Professor Mambura. It is titled Sensitization and Characterization of Magnetorheological Nanofluid, or MRNF, for optimum heat transfer in solar collectors. So let us some graphical abstract. This graphical abstract. You see how from how we get nanofluid from nanoparticles, and after that how to produce mRNF from nanofluid, and finally how to use this mRNF in solar collectors. This is in general give us an idea of our
Ahmed, can I interrupt? Ahmed,
hello?
Can I interrupt?
Yes.
It looks like you're having internet issues. Maybe stop your video and then present. Maybe it will be better. So stop video. Yeah.
Okay.
I'm suggesting you stop your video and then just present. It looks like you're having internet issues.
Okay.
Can stop video and present.
Now it's okay?
Yeah.
Yeah, I stopped the video. It is okay now? Are you hearing me, Professor? Hello?
Proceed.
Okay.
Proceed.
So that is my the title.
Continue.
The title is sensitization and characterization of magneto used as heat transfer fluid in solar thermal collectors. So this in the first in the graphical abstract, you can say that how nanofluid from nanoparticles. After that, how to produce also the mRNA starting from nanofluid solar collectors. An introduction. What is nanofluid? Nanofluid is just like from 1 to 10 or 1 to 100 nanometers injected inside base fluid. This base fluid can be water, oil, and so on, magnetic or non-magnetic. Example here, titanium oxide injected into water. This is type of nanofluid. This nanofluid also have all the nanofluids have rheological behavior. That means that the relation between the stress and deformation is not linear. It means that if you shake this nanofluid, it may lose its viscosity may change. Second point is hybrid nanofluid. Hybrid nanofluid is just combination of nanofluids. You can say some type of particles, 2 or 3 suspended in base fluid, or you can just make 2 base fluid and inject 1 nanoparticle inside it. So this is called hybrid nanofluid. So by dispersing this nanofluid into base fluid, there's another thing, is viscosity. This will increase. So in my case, when I'm working in solar collection, increasing K is desirable because it will increase the heat gain. But increasing the viscosity is not desirable, especially in applications such as in follow application, because it requires more pumping. Because it's desirable, but here in my application, I need less less viscosity. So how to adjust the viscosity? So how to reduce the viscosity and keeping the thermal conductivity as it is or high. So we can just expose this nanofluid to magnetic. This nanofluid to magnetic field is known as magnetorheological nanofluid. So magnetoroyalogical nanofluid is just nanofluid, but exposed to magnetic field. The example here is iron oxide 3. After that, exposed to magnetic field. So what is the statement of purpose? I need here from my research, I want to synthesize and characterize and test some stable mRNF to be utilized in thermal collectors. And also I need to establish or to predict the value of viscosity for this mRNF. This is a statement of purpose on using this MRF in solar collectors. Methodology. I can prepare mRNF first by preparing nanofluid. After that, I can exposing it to magnetic field. So preparing the nanofluid, I can just purchase or buy a nanofluid from the market and prepare the nanofluid. The nanofluid can be prepared by two ways. One is bottom up, or called one step method, and the second one is two-step method or top-down method. In case of bottom up, normally when we need to produce nanoparticles from gases or liquid material. So instead of producing nanofluid, after that solidifying them, we can just evaporating instead of producing the nanofluid. After that injecting, we do the two things only in one step. Only in one step. That is why we call it one step, but just by evaporation. The second, the two-step or top-down is by adding the nanoparticles first, and also after that we can add this add the nanoparticles first. After that, adding or injecting inside any base fluid, just here like ionized water or any base fluid. After that, we can do some like sonication by stirring or mixing or vibrating or something like that. So we get the nanofluid in two steps. A nanofluid, after that, we need to characterize the fluid, means to know the quantities of this, the concentration of the nanoparticles, the impurity inside the nanofluid by using some techniques, just like particle size analysis, neutron activation analysis, and TAM, and so on. Also, we need to study the stability of this nanofluid by checking its zeta potential, which is very important. Zeta potential is just like electropotential between the moving fluid and the fluid adjacent to the wall. So we're seeking high zeta potential to avoid aggregation or agglomeration. After we fabricating our nanofluid, now we need to synthesize the MRI fluid nanofluid. Just that nanofluid fabricated by two-way or one-way method, just to expose this nanofluid into magnetic field with some direction. So this fluid inside, this nanofluid inside the magnetic field, we call it mRNF. So we can just control by controlling the different parameters of magnetic, means the direction, the things, and or the type, the viscosity of the nanofluid. So we keep as you see here, when you expose this, there's some formation or chain formation. That means that this will normally will increase the viscosity, but by changing the direction, changing the value, strength, something like that of the magnetic field, we can change also the viscosity. And after adjusting the viscosity, now we can use that for solar thermal application, just in PTC, parabolic trough collector, in FPC, flat plate collectors, and vacuum tube, and so on. Expected result. Since now I didn't get the time, or even I not yet started my lab, so I didn't have graphs. But as soon I will start my research in the lab, and I will drawing these graphs. So expected results, high heat gain will be 10 by using mRNF in solar collectors, because when you increase the thermal conductivity, automatically will increase the heat gain. Also, from this result, from this abstract or from this research, I need to put some formula, some simple mathematical formula to express or to predict the value of viscosity in terms of other parameters, just like how viscosity, thermal conductivity, temperature, dimension of the nanofluid, concentration of the nanoparticles, the zeta potential, and also the direction of the magnetic field and all the other values of the magnetic field. I need also to make some comparative study of the effect of magnetic field on a magnetic field and non-magnetic.
3 minutes left for you, Ahmed. You have only 3 minutes left.
Conclusion. Conclusion now. It is a very new branch of science and has which is dealing just like combination between fluid mechanics, magnetic and electrical study. All this has more promising application, just like in energy, in biomedical, in tribology, in cooling and vibration, and so on. Also, mRNF has an adjustable viscosity, because you can just adjust the viscosity by changing the parameters direction of it. mRNF is an excellent observing medium because it's good optical characteristics, so we can use it for. Also, it has good stability, because till now there is some research in this stability, because it's shown that the zeta potential is very high. Means negatively or positively is very high. So also it has high density and high convective heat transfer, or H, which increase of course the efficiency of the thermal device.
Thank you, Ahmed, for nice presentation. Our members, we have 15 minutes to ask questions to the 3 presenters of session number 7. Questions, discussions, you're welcome. Questions, discussions for the 3 presenters of this session? Any questions? Question to Mwende or Ahmed And Charles.
Hello, Dr. Samiji.
Yes, I
Hello.
can hear.
Yes, I want to ask Ms. Mwende a question. Have you, is Ms. Mwende listening? Have you been able to can you give us the view of your effects of the structure and optical, on the optical and electrical measurements, the way you have presented it in numbers, you know, how do they differ from one structure to the other? Hello?
Ms. Mwende, can you attend the question, please? Mwende? The question is directed to you. Is Mwende still around?
Maybe we can discuss with the supervisors on that project. I just want to know the effects of the structure on the numbers, in particular the electrical properties of the organohalide perovskite films.
Through the chair, I think she has muted her mic. And there are also some more questions in the public chat.
I think the question was addressed to Mwende.
Yeah, it's about halide perovskites, the films. I want to know whether you are doing the dark current characteristics. What is that she has found with the dark current characteristics? How many structures have she played around? Oh, it's like she's not there.
Maybe the supervisor can help on that. Professor Manzai?
Yes, ma'am.
Maybe you can the question in the chat so that she can follow on that.
Okay, thank you very much, ma'am.
Thank you. Another question to the presenters of the session. While Professor Manza is putting a question on the chat.
Electrical characteristics results.
There's some questions we have posted on the chat. Presenters, can you attend those questions, please?
The problem with Ms. Mwende is that she has muted her mic.
Mwende, can you unmute your mic, please?
Okay. Let me just give her some kind of thinking that I heard about this is that when you speak about the effects of formation methods on the optical and electrical properties, I wanted to check if you had different band gaps of this material that you have made and your dark current characteristics. Which ones did you present? Did you present your the barrier height or anything similar related to your ideality factor for the dark characteristics? Or have you gone on to finalize the complete solar cell on that? Because according to the topic here, you are speaking only of the films, the thin films. That's what I was interested in.
Thank you, Professor Manzai. I think he will take on that. And there's another question from Mogunde, which was posted in the chat. Can you attend that one as well, Mr. Mogunde?
Yes, I see on slide number 13. Dr. Dari, you are sharing the slides because from my end I cannot, but still I can respond to his inquiring how I was extrapolating the dotted lines to 3.5 cutoff. That's where I believe he's asking about the band gap, which was coming to 1.86 electron volts. If it can be clarified. Slide number 13. Yes, he's talking about 3.5. Yeah, this one, because of the space, actually I could have gone to 4. It goes even up to 4.5. This is just an editing. I cropped because the entire service was not helpful to this point. So it is bigger than that, I accept. It is even up to 4, but it is not assisting anything. There is no significant data worth recording. So thank you.
Thank you.
Hello. Yes, I have another question. Your green dye.
Yes.
What was the root of your green dye? There was the green dye and there was a black dye.
Yes, there was carbon.
Okay.
So it is a mixture.
Yes, you have mixed them, but I'm interested in the green one only.
Okay, the green was extracted, the extraction point or what?
Can you explain more about this dye, the green dye? Because I'm interested in using the green extracts onto semiconductors for improving the light harvesting properties of the semiconductors.
Yes. So the green constituent is believed to contain compounds which eat like anthocyanins, chlorophyll,
yes,
which trap the energy from the sun for their survival. So this was, and they are also resilient. These two types of grasses, they are resilient to seasonal variations, adverse seasonal variations. So this behavior is likely to be transferred to solar cells, dye-sensitized solar cells. So in the processing of these green components, I did not heat. There is no heating. There is no destruction of anything there. So they were naturally crushed, and then everything was preserved at the natural state.
Thank you. Have you studied the dye separately as a single entity before you start looking at it mixed with the carbon?
Yeah, without mixing with the carbon, there is a result in slide number 11.
Can you go to that slide, please?
So where you have the dye, U, sample label U.
Okay, U, yes.
Yes, that is when there is no mixture completely.
Okay. Mm-hmm.
Yeah. And when you have carbon alone, that's what you expect.
Okay, U is for the green dye.
Yes, green dye. So
and then
to
which
enhance,
one is carbon?
Yeah, pure carbon is P.
Oh, okay.
Yes.
All right, thank you very much for clarification. I'm actually very interested in this green dye. So I hope to get an email and send to you and check. So you say it's natural, complete natural from some trees or something?
Yes,
okay.
Yes.
I'm interested in that green dye to extract it instead of buying some of these dyes or extracting them from different methods that we use for cyanobacteria or phycobilisomes.
You're welcome. We can
Thank you
still,
very much.
there are more experiments to be performed to ascertain the stability of the dye. So it's an ongoing work. You're welcome.
Yes, thank you very much.
Okay.
Thank you, Charles and Professor Manzai. So Monday is not around. Many questions has been addressed to her. Any other question to the other presenter like Ali? We have only 2 minutes time.
It's a couple now. No. Talking.
Okay, thank you all presenters of the session. Also like to thank you, Professor Waita. Dr. Waita, as the rapporteur of the session. I hand over now to the chair, Professor Mabora.
Okay, thank you very much, Dr. Samichi and Dr. Waita for managing that session.